Assalamualaikum and salam sejahtera. In this presentation, we will discuss the numerical solution of Newton's law of cooling using Euler and Runge-Kutta methods. Differential equations are widely used to model many real-life phenomena, especially in engineering and science, such as heat transfer, population growth, and fluid flow. However, many differential equations cannot be solved analytically. Therefore, numerical methods are used to obtain approximate solutions. In this study, we focus on Newton's law of cooling as a real-life application to demonstrate the use of numerical methods. Newton's law of cooling describes the process of heat transfer between a hot object and its surrounding environment. According to this law, the rate of change of temperature of an object is proportional to the difference between the object's temperature and the ambient temperature. This model is commonly applied in the situations such as the cooling of hot beverages or heat dissipation in engineering systems. The mathematical model for Newton's law of cooling is given by the following differential equation. Here, T represents the temperature of the object, T subscript EnV is the surrounding or ambient temperature, and lastly, K is the cooling of constants. This cooling problem is formulated as an initial value problem. The initial temperature of the object is assumed to be 90 degrees Celsius at time 0. The ambient temperature is assumed to be 25 degrees Celsius, which represents a typical room temperature. The cooling constant K is assumed to be 0.15. This value represents a reasonable cooling rate and allows us to focus on comparing the numerical methods rather than the experimental measurements. Since this is an initial value problem, numerical methods such as Euler and Runge-Kutta are suitable for obtaining approximate solutions. This method will be explained in the next part of the presentation.
Next, I will explain the Euler method, which is one of the most basic numerical methods used to solve first-order differential equations. The main idea behind the Euler methods is very simple. We use the slope or rate of change at the current point to estimate the value of the solution at the next time step. Mathematically, the general Euler formula is given here, where Tn is the current temperature, h is the step size, and the last one represents the rate of change of temperature. By repeatedly applying this formula, we can approximate the solution over a period of time. In this project, we apply the Euler method to Newton's law of cooling. Newton's law of cooling states that the rate of change of temperature is proportional to the difference between the object's temperature and the ambient temperature. Here, K is the cooling constant and T ambient represents the surrounding or ambient temperature. When we apply the Euler method to this differential equation, the formula becomes as given. This means that the next temperature depends on the current temperature, the difference from the ambient temperature, and the chosen step size.
For example, suppose the initial temperature is 90 degrees Celsius and the ambient temperature is 30 degrees Celsius and the step size is 1 minute. Using Euler method, we can compute the temperature step by step and obtain an approximate temperature at each time.
For this example, the Euler method was implemented using Python, and the table shows the estimated temperature values at each time step. As we can see, the temperature decreases gradually over time, which follows Newton's law of cooling. However, since Euler method is a first-order method, the accuracy depends strongly on the step size. The main advantage of the Euler method is that it is simple and easy to understand, making it suitable for introductory learning. However, the disadvantage of this method is its low accuracy, especially when the step size is large, which can lead to significant numerical error. Due to these limitations, a more accurate numerical method known as the Runge-Kutta method will be used. This method improves accuracy while using a similar step-by-step approach.
Runge-Kutta method, specifically the fourth order Runge-Kutta or RK4, is numerical method used to approximate solution of ordinary differential equation. It is commonly applied when the analytical solution is difficult or impossible to obtain. Unlike simple method, RK4 improves accurately by averaging the slope or zero point within the single time step. One major advantage of the Runge-Kutta method is high accuracy. As it is for other method, this means the numerical method is significantly smaller compared to first order methods such as Euler method. In addition, RK4 remains stable when the large step size is used, making it efficient and reliable for numerical simulation. Compared to Euler method, which uses only one slope per step, the RK4 method uses the 4 slope, which allow RK4 produce results that are much closer to exactly solution, especially for problems involve rapid change such as cooling process. For a differential equation in the form R dt over per dt equal to FDT, the RK4 method calculate for different slope which are denoted as K1, K2, K3, and K4. The first slope K1 represents the rate of change at the beginning of the interval. The second and third slope K2 and K3 estimate the rate of change at the midpoint of the interval. And the fourth slope K4 estimate the rates of change at the end of the interval. These four slopes are then combined using weighted average to compute the next value of the solution. In this study, the Runge-Kutta method is applied to Newton's law of cooling, which models how the temperature of an object change over the time relative to its surrounding environment. By substitution of cooling equation into the RK4 formula, we can numerically estimate the temperature at each time step with improved accuracy.
For this part, I will explain the programming, implementation, and graphical results of the numerical methods. The simulations were implemented using Python with the help of NumPy for numerical computations and Matplotlib for data visualization. The mathematical model used is a Newton's law of cooling, which is a first-order differential equation describing the rate of change of temperature with respect of time. Both of the Euler method and the fourth-order Runge-Kutta method were implemented using the same parameters and step size to ensure a fair comparison. First, the Euler method was implemented. This method approximates the solution by using the slope at the current time step to estimate the temperature at the next step. Although the method is simple and easy to implement, its accuracy strongly depends on the chosen step size. Next, the Runge-Kutta fourth-order method, or RK4, was implemented. This method improved accuracy by calculating 4 intermediate slopes at each time step and combining them into a weighted average. As a result, RK4 provides a more accurate numerical approximation compared to the Euler method. This graph shows the temperature change with respect to time for both numerical methods. From the graph, we can observe that the Runge-Kutta method produces a smoother and more stable curve compared to the Euler method. The Euler method shows a larger deviation, especially when a larger step size is used. In contrast, the RK4 method closely follows the expected cooling behavior, indicating higher accuracy. Therefore, we can conclude that while the Euler method is simpler, the Runge-Kutta method is more reliable for solving Newton's law of cooling when higher accuracy is required.
This slide combines the effect of step size with error and accuracy analysis. Step size h represents the time increment used in the numerical solution. When a smaller step size is used, the accuracy improves but more computation are required. On the other hand, a larger step size reduces computation time but increases numerical error. The Euler method is a first-order method, so its error is directly proportional to h, making it very sensitive to step size change. In contrast, the Runge-Kutta method is a fourth-order method with much smaller error. As a result, RK4 produces smoother, more accurate, and more stable solution compared to the Euler method.
In conclusion, Newton's law of cooling can be modeled using differential equation and solved numerically. When analytical solutions are not practical, numerical methods such as Euler and Runge-Kutta are useful alternatives. The Euler method is straightforward and suitable for basic understanding, but it lacks accuracy. On the other hand, the Runge-Kutta method provides much higher accuracy and better stability. Finally, the choice of step size is very important as it directly affects the accuracy of the numerical solution. Overall, RK4 with a smaller step size gives the most reliable result. Thank you.